Welcome. Today we are going to continue our look through Chapter 9, and today we are going to focus on a technique of organizing the electrons that occupy the orbitals that we learned about in the quantum mechanical model in the last segment. So there's two sort of ways that we can look at this or draw it out, two different sort of systems. They essentially do the same thing, but just little different techniques. One is called electron configuration, which is sort of the primary one, and orbital diagrams. These are the other ones. Again, they show essentially the same information, just in a slightly different way. So if we take, for example, hydrogen, right? Hydrogen, the first element, element number 1, it has one electron, right? Now that one electron is going to be located in the 1s orbital, right? So remember, that's the lowest energy orbital. That's the orbital that the electrons are going to occupy first. So if we wanted to show that in terms of the electron configuration of a hydrogen atom, the way that we do that is we write out what the orbital is, right? So it's the 1s orbital. And then we use a superscript to show how many electrons are in that orbital. So we show one electron in the 1s orbital by writing out 1s1. And that becomes the electron configuration of a hydrogen atom, right? Since that is the only electron that we have in there. Now, if we were to show that same information in an orbital diagram, it would look something like this, right? Where in an orbital diagram, we use boxes, right, to represent the orbital itself. Underneath the box, we draw what the orbital is. So we have the 1s orbital, and we use half arrows to represent the individual electron. So in this case, we have the box representing the 1s orbital with one electron or 1.5 arrow in it representing the one electron. So this again would be another representation of that, showing where that one electron is in the hydrogen atom. So in these orbital diagrams, the direction of the arrow is part of the information, right? And in any orbital, there can be one electron pointing up and one electron pointing down, right? This represents what we call the electron spin. So we say spin up or spin down. And spin is a fundamental property of electrons, which in this class we're not going to get any deeper into that, but it's represented by whether the arrow is up or down. Now, one of the rules that govern how we put electrons in is called the Pauli exclusion principle. So what the Pauli exclusion principle states is that orbitals may hold no more than 2 electrons. That's the first key point. So any orbital of any type can only hold 2 electrons, and they will have opposing spin. Now, so if we're drawing out the orbital diagram, we can show that opposing spin as one would be up, one would be down. Now, that information about spin isn't shown in the electron configuration, right? It's a simpler way to express it. So let's kind of look at the big picture. So if we take all of our orbitals and we lay them out. So if we start with the lowest energy orbital, right, we have the 1s orbital, lowest energy down here. As we move up, we have the 2 second level. We have the 2s and the 2p. Now, within a level, so within the second level, the s orbital is always a little bit lower in energy than the p orbitals, and so we are going to fill the s orbital of a level first, right? So the s orbital of a level fills first, followed by then the p orbitals. And notice when we write out the p orbitals, we have a set of 3, right? Now you can see here as we move up to the third level, we have the S, we have the P, and we have the D, right? The D would be even a little bit higher energy than the P, and so they would fill later. Now, the key thing to note here is this area right here. And what we want to notice is that the 4s orbital is actually lower in energy than the 3d orbitals. So even though it's in a higher level, it's actually lower energy than those d orbitals, in this case the third level. Now what that means for us is that the 4s orbital will fill first. So 4s will fill before the 3d. And this is a pattern we see repeat over and over again. We see up here in the 5s, right? It's a little bit lower than the 4d, so the 5s would fill before the 4d. So once you get up to where there's the presence of d's, we'll see this pattern where the s orbital of the next level fills before the d of that level you're on. So we have this energy order, right? And the orbitals will always be in this same energy orbit, this same energy level. So what that means is the orbitals will always fill in the same order, starting at 1s and then working our way up through progressive energies. So if we can get this order down, right, or understand this order, then we know how the electrons are going to fill. So let's take a look at some atoms that have more electrons. So if we just move through the periodic table, so we move to the second element, helium, atomic number 2, would have 2 electrons. We would see both of those electrons would pair up in the 1s orbital. Notice one is up, one is down. Now, according to the Pauli exclusion principle, right, this is all of the electrons we could fit. So at this point, the 1s orbital is filled. So we can see that if we move to lithium, right, element number 3, 3 electrons, we can see that third electron goes into the next orbital in our energy order, and that's the 2s. So we would have a configuration of 1s2, 2s1, right? Notice the superscripts here are going to total up to the total number of electrons. In the orbital diagram, we would have 2 electrons in the 1s paired up. We'd have that single third electron in the 2s. Now, if we keep going, we can see this pattern. We jump over a few to carbon. Element number 6 will have 6 electrons. If we look at the configuration, we're just going to go in order, right? So the first 2 electrons go into the 1s. The next 2 electrons go into the 2s. The next 2 electrons go into the 2p. Now, this brings up another point about filling these. When you start filling a p set of orbitals or a d set of orbitals, notice that all of these orbitals are the same energy. So the electrons will always fill them singly first rather than pairing up, right? So you notice these 2 electrons are going one into each of these first 2 instead of pairing up in the first one. This is what's known as Hund's rule, right? Which essentially says that when filling orbitals of equal energy, electrons fill them singly first, then pair up. Okay. So we have Pauli exclusion principle, we have Hund's rule. These are the two rules that govern how we fill these orbitals. So if we kind of continue this trend and move through the rest of the second period, so we move to elements 7, 8, 9, and 10, we can see we progressively add 1 electron. So the 7 electrons of nitrogen, there'll be 3 in that 2p. Then we'd have 4 in the 2p, right? And so now we'd have to start to pair up. then we'd have 5, and then we'd end up with 6. Notice in our electron configuration, the subscript on a p can go up to 6, right? Because at that point, we filled in the total number, all the electrons in the p orbitals. So we have 3 orbitals, can hold 6 electrons. Okay. So then we would just continue that pattern. So in theory, we can do that any element on the periodic table. We know the total number of electrons. We're just going to follow our order and fill up. When we're filled, we move on to the next one, etc., until we run out of electrons. So, in summary, we have 3 basic points that will guide us in filling up our orbitals with the electrons in our atom. The first one is we always follow the order of energy, right? So lower energy orbitals fill before higher energy orbitals. So it always starts with 1s, and then goes to 2s, and then goes to 2p, then to 3s, etc., right? So we just follow that energy order. Any orbital can only hold no more than 2 electrons with those 2 electrons having opposite spins, right? The Pauli exclusion principle. Right? An orbital can have no more than 2 electrons, and those electrons will have opposite spins. When we have orbitals within a set that have the same energy, so a p set of orbitals or a d set of orbitals, they fill singly first before they pair up, right? This is what's known as Hund's rule. So we follow these sort of 3 guidelines and rules, and we can fill or come up with the electron configuration, the orbital diagram of any element. So let's look at a couple examples and point out some other vocabulary that we want to come in contact with or we want to be familiar with. So let's, for example, look at the electron configuration of silicon. So as we can see here, silicon, if you were to look on the periodic table, right, has 14 electrons, right? Element number 14. So when we put those 14 electrons in there, right, the first 2 go into the 1s, the second 2 go into the 2s, the next 6 go into the 2p, right? The next 2 go into the 3s, and then the 2 remaining ones would go into the 2p. Right? So we have our 14 electrons drawn out in our electron configuration. Now, we have 2 different types of electrons in an atom, right? We have what are called the valence electrons. And valence electrons are the electrons in the outermost principal shell, or in other words, the biggest N number, right? So then we're looking at silicon, the electrons in orbitals that are in the 3rd level, those are what we call the valence level, right? Because those are the electrons that are the most removed or the farthest away from the nucleus. All of the other electrons, all the electrons in lower energy orbitals, are what we call core electrons. So silicon would have 10 core electrons and 4 valence electrons, right, making up its 14 electrons. And we can see this, for any element that we do. So we got selenium. So we can see its 34 electrons are going to go in as we order, right? So we go 2s, 2p, 3 up to 3p now. Remember in our energy order that after the 3p comes the 4s. Then we fill the 3d, and then we go back to the 4p. Now our valence electrons here are defined by, again, the highest shell, or the highest principal quantum number. In this case, it's the 4. And so any electron in that 4th level is going to be part of the valence. So the 2 in the 4s and the 4 in the 4p make up 6 valence electrons in selenium. So even though these are right next to each other, even though they're not right next to each other, they are part of the valence. But notice the 3D, are not considered part of the valence electrons because they're in a lower principal shell. So that's, really important. And the reason we make this distinction is the valence electrons are the important electrons, right? These are the outer electrons. These are the ones that are going to be involved in the chemical reactivity, right? In bonding, in reactivity, when elements form ions, etc. These are going to be the electrons that are involved. It's the valence electrons that are important. The core electrons are stable, kind of like the nucleus, right? They're held, they're filled, they're stable. They're not really going to be involved in the reactivity very much. So if we take this information now, and we take the first 18 elements, and we put on their valence electrons, right? And we sort of group them as we would on the periodic table, we can start to see some patterns. So the first pattern is pretty obvious, right? It's that as we go from element to element, we're simply adding one electron to our valence electron count, right? So as we go, from across the second period, we go from 2s1, 2s2, then we go into p1, p2, p3, p4, right? So every time we move from one element to another, we add one more electron. Now, the other thing that starts to stand out here is as you look at columns, so groups, we notice that they have the same pattern and same number of valence electrons. So if I look at the alkaline metals, for example, here, right, they all have a valence electrons that have an S1. And so they all have one valence electron, and it's in an s orbital. If we go over to, say, the halogens here, right, notice all of these have an S2p5, right? Whether it's 2s2, 2p5, or 3s2, 3p5, right? So they always have that same configuration with yielding 7 valence electrons. And we can see that for the other groups as well. Now, something that I'll mention again later, but I'll go ahead and mention it now, is this is where understanding the group numbers and the notation that we use can become a little useful, because notice that the halogens are group 7, and they have 7 valence electrons. The alkaline metals are group 1, they have 1 valence electron. So for the main groups on the periodic table, so that's the first 2 and the last 6, right? Not the transition elements. The group number equals the number of valence electrons. So this can be a little shortcut once you understand it. If I give you an element, say sulfur, and you say, oh, that's in group 6, it must have 6 valence electrons, and then you could write out the configuration to confirm that. But if you just need to know the valence electrons, how many there are, you could easily know that from its location in the periodic table. Now, if we expand out to the entire periodic table, we can now start to divide the periodic table into groups, or into segments based on where the electrons are at. So notice group 1 and 2, when we were filling those, we were always putting electrons into an s orbital, right? So whether it was the 2s in the second period or the 3s in the third period, etc., right? So this is what's known as the s block, because the electrons that we're putting in there, the end electron is always going to be in an s orbital. The other half of the periodic table, these 8 groups, or these 6 groups here, right? This is what's known as the p block, because those 6 electrons that you're putting in as you go across are all going into a p set of orbitals, right? So as we go across, we go p1, p2, up to p6, right? And then the p orbitals are filled, and we reach the end of the p block. The transition metals represent or make up what we call the d block, because as we progress through these, notice 10 columns, we're putting the electrons into our 5 d orbitals, right, which are going to be able to hold 10 electrons. So that's the d block. The lanthanides and the actinides represent what we call the f block, and notice it's 14 elements long, representing the 14 elements, the 14 electrons that would fill up the f block, or the 7 orbitals that come in an f set of orbitals. So we can look at the periodic table and understand where those last electrons are going to be at. What orbital are we going to be filling during that particular element? Now, writing electron configurations. So there's lots of ways to learn how to write electron configurations, right? One is we just sort of remember the order. We see how many electrons are there, and we just start filling up the electrons, right? And the more of these you do, you start to say, we're going to fill up the 1s, then the 2s, then the 2p, then the 3s, then the 3p, and that's fine. But as we get to a little bit bigger, sometimes it's useful to have a little guide. And we don't need any sort of additional guide if we understand the periodic table and these sections of the periodic table that we were just talking about, these blocks. So this is, if we look at the periodic table here, and we do say, for example, phosphorus. So phosphorus has 15 electrons. So if I start at the beginning of the periodic table and I go left to right across the periods, so I know my first 2 electrons go into the 1s, right? It's the s block. Once we get to the end of a period, we go back to the beginning and we go through the second period. Well, first we go through the s block on the second period. That's the 2, right? So we go 2s1, 2s2, then we would go across and fill up the 2p, 2p1, 2p2, 3, 4, 5, 6, right? And we get over to 2p6. Then we're at the end of the second period, we go back to the third. So now we're in the third period, we're filling the 3s. So we go 3s2, right? So at this point, we have 12 electrons. So we have 3 more left, and we go across, and we go 1, 2, 3 steps into the 3p, and we reach our element phosphorus. So we got 3p3, okay, which gives us our element. Now, so that's the key. So the idea that we can use when we start to do this. Now, a couple things to keep in mind here is that we can do any element that we want to on this. And if we use the periodic table to follow us, it'll also help us. So let's say we wanted to do bromine, right? So bromine is right here. Right? It's element 35. So if we do bromine, so we have 35 electrons, and we're going to go through the same pattern. We're going to go 1s across the 1s. We're going to move down to the second period. We're going to fill up the 2s, then go across the 2p's. So now we're up to neon, element 10. So then we go to the 3s. We do the 3s2. Then we go across the 3p. We get to argon, right? And we're up to 18 electrons. Now, one of the key important parts here is that if I follow the periodic table, once I get to the end here, then I will immediately have to go down to the 4th period. And what's I do first? I go through the 4s. So this is a good way to remember that after 3p comes 4s. And those next 2 electrons are going to go into the 4s before we start hitting what would be the 3D? So the D level is always one period below where the S and the P are. So we're in the 4th period, but this is the 3D, right? And the 5th period, this would be the 4D, etc. So we're going to go across the 3D, right? And we get 3D 10, right? So we're at 30 electrons here. And bromine is, 1, 2, 3, 4, 5 steps in. And so we're going through the 4p5. So this would be the electron configuration of bromine. Now notice the valence electrons here, right, are going to be all the electrons in the 4s, or in the 4th level, right? So notice we have the 4s2 and the 4p5, right? This gives me my 7 valence electrons, right? Understanding that bromine is a halogen, it's in group 7, we would expect 7 valence electrons. Now, one thing we notice here with we get down to stuff like bromine is that these configurations can get quite large. So we have a shortcut that we can use, and it's called the noble gas configuration, right? So what you can do is you can take the element that comes before any of these, right? And you go backwards to the nearest noble gas. So for bromine, we're going to go backwards to the noble gas that comes right before it. That's going to be argon right here. And we could use the symbol of that noble gas to represent all the electrons up to that point. So up to the 3p, those 18 electrons are actually argon. So I can use just the symbol argon to represent those 18 electrons, and then just write what comes after that. So 4s2, 3d10, 4p5 would be another way to write the electron configuration of bromine. So we have this shorter way that we can write configurations using what we call a noble gas notation, right? Where we take an element, so for phosphorus, right, we were here, so the noble gas that came right before it was neon. So neon can stand for the first 10 electrons up to neon, and then we write what's left, 3s2, 3p3, and so here we have this shortened noble gas configuration for phosphorus. So this only becomes really important when you start getting to bigger ones where you don't want to write it all out. So these are just two different ways to write out the configuration. One is a little bit shorter than the other. Now, so what are the things that we've started to notice here? Well, big one here is that elements in the same group have the same number of valence electrons. And this is a way that we can explain what we observed far back as Mendeleev in putting together his periodic table, that elements in the same group have similar chemical properties because now we know because they have the same number and configuration of valence electrons. This is what explains why, fluorine, chlorine, bromine, iodide tend to be similar, because they all have that S2P5, all have those 7 valence electrons. Or why the alkali metals tend to have similar behavior, because they all have that 1 valence electrons located in an s orbital, etc. So this explains some of these behaviors. Things like, why do they always form the same ions? Well, because if we look at the periodic table, right, all the alkali metals, they all have to lose 1 electron to get to be like a noble gas, right? And remember, they're trying to get to be like a noble gas because, remember, noble gases are stable, right? They don't react. So there is something particularly stable we'll see about a noble gas electron configuration. And elements are trying to get there. So elements form the same ions. They have same reactivity. And it all states back to this idea that they have the same arrangement and number of valence electrons.